Okay. So we are in our last section, the quadratic formula and complex numbers. Sorry, let me adjust this. Okay. The quadratic formula and complex numbers. So here we have trinomials. Okay, sometimes A is 1, sometimes A is not. And either we don't know how to factor, or we can't remember, or we're not sure if our answer is right, or we can't factor at all. So how are we going to solve this equation? Well, you would complete the square. If you complete the square and then get x by itself, it creates a formula. And in class, I'm going to show you on a PowerPoint, or you know what, I'll attach the PowerPoint in classwork, and you can look at it, or I'll show you in class, either one, remind me. But the process of how you come up with this formula, someone just didn't come up with these letters and say, okay, here you go. It's actually completing the square. So instead of completing the square every single time, we are going to just substitute these letters, A, B, and C, into this formula. So you could bring everything to one side. If it's not, you could simplify and bring everything to one side. It doesn't matter. Just pick one and use a quadratic formula. So let's just use number 1. If you're not good with number 1, then you can continue to pause the video and try number 2 and number 3. So number 1, 2 is your A, 5 is your B, C is -3. So opposite of B plus or minus the square root of B squared minus 4AC all over 2A. And some of you in middle school, I think you had Mr. Tillich or another teacher, and they taught you to memorize this by saying it like Pop Goes the Weasel. So they would say x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Sorry, but that will help you remember it, okay? And this isn't going away. This is going to stay around for pre-calc and calc and so on. So you substitute all your numbers in and then you simplify. So where your zeros or solutions or intercepts are, or roots, sometimes they're called, is going to be 25, that's -8, -8, and -3 is going to be a positive 24 all over 4. So it's going to be -5 plus or minus, excuse me, the square root of 49 over 4. Immediately, I like to separate them so I can get, if I'm getting a decimal, and say, okay, that's going to be 7 over 4. Okay. Oh, so it's 5 plus 7 over 4 or 5 minus 7 over 4. Either one. And you're going to get 12 over 4 and -2 over 4. So your answers are 3 and -1/2. You don't have to separate them if they're not going to simplify, but if one part's going to simplify versus the other, you can separate them, or you can just put them right back where they were. So your answer is 3 and your answer is -1/2. That means if I substitute a 3 in here, I'm going to get 0. If I substitute a -1/2 in here, I'm going to get 0. And that's an easy way to solve. So if I were to graph this at -1/2 and at 3, there's the quadratic. Okay. All right. I want you to try these next 3. So go ahead and substitute them into the quadratic formula. I kind of already did it, but I'll let you pause and go ahead. Okay, and now you're going to simplify. Okay, so I'm starting to clean them up. We have 3 situations. They're pretty similar. -4 plus or minus the square root of 8 over 4, -4 plus or minus the square root of 0 over 4, and -4 plus or minus the square root of -8 over 4. Okay, so we have two irrational solutions, two solutions. They're real numbers, but they're irrational. Here, when I had 0 under the square root, we had -1 plus 0, -1 minus 0, so we just have one solution. And here, when I had -8 under the square root, we have no solution. Okay, so these are three different situations. So what would the graphs look like? The graphs would look like crossing at 2 points, crossing or being tangent or touching at 1 point, and just kind of floating above, not touching at all. Okay, I'm not sure how exact these graphs are, but those are three situations that you're given. So it said which equation had two real solutions the first, which equation had one real solution the second, and which equation had no real solution the third. It says without using the quadratic formula, the entire part, you can tell whether or not an equation will have none, one, or two real solutions. Look at the previous equation and what inference can you make? So what can you say? Everything's the same, but what? The number under the square root. So if the number under the square root is positive, you're going to have two solutions. If the number under the square root is 0, you're just going to have one solution. And if the number under the square root is negative, you're not going to cross the x-axis at all. You'll have no solutions, or real solutions, I should say. So the inference you can make is down here, so you don't have to write it. It says if that b squared minus 4ac part is greater than 0, like the number 8, then you're going to have two real solutions. If it is blank, then you'll have no real solution, so if it's negative. So this is the number under the square root. I don't want the square root part, I'm just saying that number underneath it. Ooh, whoa, I'm sorry. Okay, and b squared minus 4ac equals 0. That's one real solution. Okay, this is called the discriminant. So even when the discriminant is negative, though, there's actually two solutions, they're just not real. We identify the solutions as not real. However, there's a number system called the complex number system. Okay, that includes all real numbers and all real non-numbers. So if you're a real number, you're in that system too. Real number system is just what we came up with. Theoretical math eventually is applicable math. So this is important. Non-real numbers, just numbers with I in it, are imaginary. And we briefly talked about I. We said the square root of -1 is referred to as I. So you can also say if I have the square root of -r, rip out that -1, and it's the same thing as I square root r. You can put the I in the front, you can put the I in the back, but the problem is students tend to write it under the square root, and I want to make sure they're separated. So just kind of leave it like that. So here, it said you could rewrite it as this and then simplify. Or I just tell students, move it out. You're done. Move it out. You're done. Now, I'm just writing a positive 4i. I'm just writing a positive 3i. When you have just simplifying a square root, you're just taking the principal or the positive square root. When you're solving, you take both because it could have been those two things. Here, we're just evaluating or simplifying. And then I is 2, 2, 2, 5. Take the pair out. So it's 2i root 10. Like I said, other textbooks might have 2 root 10i. Problem is people write it under the square root sign, and that's wrong. Okay, so that's how you simplify with I. So are these in the real number system? No, but they're in the complex number system, and they're important because eventually, not eventually for all, but some numbers hop back and forth between real numbers and imaginary numbers. So this is why it's pretty cool. Okay, it says, with the quadratic formula, the imaginary number, you can find solutions to all quadratic equations. So let's just pick one of these. 6 is your A, negative 3 is your B, and negative 1 is your C. If I were to graph this, I already know it's imaginary, so it's not actually going to cross the x-axis. It's not going to do this. It's going to hover. However, I can find an imaginary number that algebraically will work. So opposite of B plus or minus the square root of B squared minus 4AC all over 2A. So I'm going to have negative 3 plus or minus the square root of a negative 15 all over 12. So 15 can't break down anymore, but you can write it like this. Why I tell students to separate it is because they have a tendency to just go like this. That's incorrect, because this 12 still belongs to this radical. You can't simplify this unless you break it apart. So if you want to leave it like this, I'm cool with that. If you want to simplify more because it's just habit for you, make sure you break it apart first and then simplify if you really want to. This is fine. This is fine. Don't do this. You can't do that, okay? But this is an imaginary answer. So does it work on a graph? No, but if I take this and substitute it back into my equation, it will work. And I'll show you in a little bit why. It says complex numbers are any number that can be written as A plus BI. So A is the real number part, and B is also a real number part because it's going to be a coefficient, and I is the imaginary. So A plus BI could be like 5 plus 3i. 5 is real and 3i is imaginary, okay? The form A plus BI is called the standard form of a complex number, and real numbers are complex forms of which B equals 0. So if I have the number 5, a real number 5, it could be back into the number system of complex number systems if I just put a plus 0i. There, it's a complex number, okay? It's also pure imaginary if your A part doesn't exist. So if I have 3i and there's no A, then it's just pure imaginary. So real number, imaginary. All right, what if I'm telling you these two things equal each other? We'll put the real parts with the real parts and the imaginary with the imaginary. Therefore, negative 3x equals 21. 4iy equals negative 16i. Divide by negative 3, x equals negative 7. Divide by 4i, y equals negative 4. Okay. Here, same thing, 2x equals negative 8, and then the i's go with the i's. They're saying these two things are equal, so what would x have to be? They're saying these two things are equal, so what would y have to be? There's nothing fancy. They're just saying, hey, can you line these up and solve? Yes, you can. Okay. On the back, what happens when we use more than one I? What happens? So if I is just the square root of negative 1 or I, we just write I. We don't write the square root of negative 1. I squared is the square root of negative 1 times the square root of negative 1. Well, if I have the square root of 2 times the square root of 2, it's just 2. So if I have the square root of a times the square root of a, it's just a. So if I have the square root of negative 1 times the square root of negative 1, it is just negative 1. So this is awesome. If I times I is negative 1, now we're back into the real number system. Now we can use i's to fill in these gaps and solve for things that were unsolvable. Okay, this was kind of a big deal. I cubed is I squared times I. Well, we know I squared is negative 1, and we know I is I, so it's just negative I. I to the fourth is I squared times I squared. Well, that's negative 1 times negative 1, so it's just 1. We're back to real numbers. It oscillates in and out. Here, I to the fifth is I to the fourth times I. So it's 1 times I, which is just I. So here we're going I. What do you think I to the sixth is going to be? Oh, it's I to the fifth times I. Well, I to the fifth is I times I, which is, oh, it's going to be a pattern. It's cyclical. I, negative 1, negative I. 1, I, -1. It's just going to keep going. So anything that is divisible by 4 is going to be a 1. Okay? So for instance, pick one of these. How do we evaluate it? I to the 100th, is that divisible by 4? Then it's just 1. Okay? I to the 40th, 41st. Well, 41 is not divisible. So let's break it down. Does I to the 40th times I? Well, I to the 40th is divisible by 4, so it's just 1 times I. So your answer is I. So you can figure out any number by doing that. Okay. All right, now simplifying. We are just combining like terms. There's nothing fancy. So if I'm adding these two things, I'm going to get -2 minus 7i. Actually, try pausing the video and doing this yourself, and then come back to it. Oh, okay, so now we're up to this part you should have been fine with. This is combining like terms. This is foiling. What am I doing here? When I get I squared, I need to recognize that I squared is a -1. Therefore, this becomes a +4. When I get negative becomes a positive, but we have an I squared, so that becomes -16. Here, I is technically a square root, and we can't have square roots in the denominator. So when we had an answer like this back in geometry or algebra 1, we multiplied the top and bottom by the square root of 2 to rationalize it. Well, what if we have something bigger than just one term on the bottom? What if we have something like 3 plus the square root of 2? Well, then we need to multiply by 3 minus the square root of 2. It's conjugate, because that'd become a 9, a +3 root 2, a -3 root 2. They would cancel, and then you get a +2, and the square root would go away. So the same thing here. If this is positive, it's going to be negative, it's going to be positive. I have a 2 plus I, therefore I need a 2 minus I. That way the i's will disappear in the denominator. Okay, so 2 times 2 is 4, 2 times I is -2i, 2 times I is 2i, and -I squared. And now why am I doing this? Because it's kind of like a rule. Either mathematicians came together, or a long time ago, certain mathematicians decided, okay, it is improper to leave a radical in the denominator. You cannot divide by something that never ends, an irrational number. So you have to rationalize it. Make it pretty. Give it a makeover, okay? And this is actually going to become a real number, 2. It's just 2. I don't know why I put the exclamation point. Okay, so you can try these 2 on your own and pause the video. All right, so multiply by the conjugate. When you FOIL, you get this. This become 5i. That's going to be a -4, so -10. That's going to be a +1. Here, don't just do this. This 5 belongs to both. So if you need to separate, if you can't simplify just by looking at it. Oh, okay, that's going to be -2 plus I. If you could just simplify it right there, that's fine too. Here, the conjugate is addition. So you're going to get 20I plus 25I squared on the top. It's fine if I is in the numerator. Just in the denominator, it's just like a faux pas, okay? It's frowned upon. So make sure when you're making your tests that you're doing it properly. And really, should I have the I in the beginning? No, I should really have the I after. Is that right? Yeah. Okay. So really, -25 plus 20I. But here, these are the same thing. And this is the same thing as this. We're just giving it a makeover. Okay? All right. If you're like, well, why are we doing that? Well, you're in honors. You know, you're in honors mathematics. We don't cut corners, man. All right? There's a page here. Okay? What is the discriminant? The discriminant is b squared minus 4ac. Okay, that's the actual part of the formula underneath the radical. It says use the discriminant to determine what type of solutions we're going to have for 2x squared plus 3x plus 2. Well, b squared is 9. 4ac is going to be 2 and 2. So you're going to have 9 minus 16, so you're going to have -7. If you have -7, that's going to be under a radical. You're going to have 2 complex solutions. I wouldn't say you would have no solution because now you know what I is, okay? They want you to solve using the quadratic formula. And you can do the same thing here if you want. But you're going to get a ton of practice in your homework, so I really suggest doing that. I wouldn't skimp on this homework. This is going to be hit hard in pre-calc. So, all right, tomorrow we will continue working on your tests in your groups. If you have questions, please email me. And that's all we're doing this week. Grade-wise is your last test. We are going to hand that in on Friday. We're going to start chapter 5, but it's not going to be graded till after the quarter. And then we're going to have your midterm next Monday. Or not next Monday, I apologize. We'll have to talk in the class of how comfortable we are at this point. But hopefully either this week, at the end of this week, or next week. Okay?